happens here? This guy says, I'm going to take this voltage and multiply it by 10. So when I measure the voltage difference between these 2 points here, I will see larger excursions, right? About 20 millivolts. So what do we call this operation here? I took a small voltage change, a small signal that was coming from the microphone, and I produced from it a large voltage swing. That's what we call amplification, right? We amplified the signal from a small value to a large value. So what we have here, this guy, is a model of an amplifier. Now, we don't know how to build an amplifier yet, right? But this says that if you could build something like this, a dependent voltage source that depended on V1 by a factor of 10, then you would actually build an amplifier. Now you can see the utility of dependent sources. Dependent sources are good for cases like this, where we want to model an amplifier or some other device, and we don't want to deal with all the complexities inside that amplifier. So we just model it by a dependent source. And if a dependent source has a factor of 10, it means that we have an amplification factor, or what we call gain, an amplification factor of 10. So we give it a signal, it gives us 10 times larger that signal at the output. Okay, so that's the idea behind dependent voltage sources. All right, let's look at an example here. So it would be good to do something like this. Here's a general voltage V1. It's just that, a voltage source sitting by itself, or a time varying voltage source sitting by itself, and has 2 terminals, that's all. And I'm going to take a dependent voltage source that depends on this guy. And the dependence is, for example, minus 2 V1. So we're going to call this V2. We say V2 is minus 2 V1. And then this goes to a resistor, called the resistor R1. And what we would like to do is plot I1 as a function of V1. Why? Just because we want to do it. Whether it's interesting or useful, we don't know. But as an exercise to understand and wrestle with these dependent sources, we're going to go over this. Okay, so here's the situation. We want to plot I1, the current that flows through that resistor on the right side, as a function of V1, which is the voltage over here. So V1 is swept, is varied slowly from 0 to infinity. And we're just curious to see how much current flows through R1. Okay, that shouldn't be that hard, right? What we know is that V2 is the voltage produced here that goes across R1. So that's great. That means that the current through R1 is equal to V2 over R1, Ohm's law. So we write I1 is equal to V2 over R1. But we know that V2 is actually minus 2 V1. That's the job of V2. V2 wants to keep its value equal to minus 2 times V1. So that's actually minus 2 V1 over R1. All right. So, sorry, I forgot a minus here. Minus here. So that's what we need to plot, right? Minus 2 V1 over R1. Okay. So it's a straight line with a slope of minus 2 over R1. And it's going this way, obviously. So that would be something like this. Okay, so the slope of this line is minus 2 over R1. And it's just as simple as that. Okay, that's a quick example for us to get warmed up. Okay, let's talk a little about another example that we can, let's see, I'll insert a new page here. Okay. Maybe I'll talk about one more electric component today. We have a little bit of time. So we're going to talk about current source. So we understood everything about the voltage source. We said the battery is a voltage source, a pretty good voltage source. It could be constant, it could be variable, it could be time varying. How about a current source? What's a current source? All right. Well, I should say at the outset that we can't really buy a current source. So a current source is an abstraction. It's a model of some device or some combination of devices that can function as we will talk about. Okay. So the symbol for a current source is a, so I have this line here for some reason. Okay, a symbol for a current source is a circle with an arrow through it. And what this says is that this device wants to draw a current in this direction and has a certain value, so we're going to call it I1. That current can be constant or it can be variable. So we say a current source is a two-terminal device, obviously. Okay, that draws a certain current. It wants to draw a certain current from here to here, regardless of the voltage across it, regardless of the voltage difference between here and here. It's an amazing device. So this device says, I'm going to draw 1 ampere of current from here to here. So if you connect this to anything, it says if you connect me to a circuit, some arbitrary circuit, right? Anything in here, I will draw a current of 1 ampere, for example, at all times under any condition. You can have anything you want. You can have a short circuit, you can have an inductor, capacitor, resistor, anything you want. I will always draw the current that I want to draw. And this voltage can be 0, can be 1 volt, can be minus 1 volt, can be plus 1000 volts. It doesn't matter. I'm going to draw that current that I want. So this is an abstraction. It's really not possible to build a current source like this, but it's a very good model to have for many of the things that we're going to do in the future. Okay, so it's important to understand that a current source wants to impose a certain current through these wires, right? It draws a current like so. And it has to have the path for that current to flow through. In particular, if I connect this current source to a resistor, then it will draw a current this way, right? Or if I have a current source going the other way, then it will push a current this way. Okay, that's what we get. Obviously, when this current flows through this resistor, it produces a voltage, Ohm's law. So if this is I1, then the voltage difference between these two will be I1 R1. If this current changes with time, this voltage will also change with time. Okay, so no problem so far. But what's interesting is that R1, meaning this voltage, can be anything. So here's an example. If I pick R1 to be 0, okay, so R1 equals 0, it's a short circuit. The current source doesn't care. It still wants to produce the current, I1. So I1 just circulates through this loop, and that's all. But how about the other extreme? The other extreme is I have I1, but I have an open circuit here. Then we have a problem, right? Because on the one hand, this current has to flow through something. This current source wants to inject electrons, right? Here, it was injecting electrons into the short circuit. Here, it was injecting electrons to the resistor. But there's no place for the electrons to go. So the circuit that you see on the right-hand side is not meaningful. That cannot happen because we are trying to equate something to zero, and that something cannot be zero, right? The current source says I want to give I1. The open circuit says I want to maintain zero current. So these two have to fight. So that is not meaningful. So we say not meaningful. Okay? Now, alternatively, we can think of it this way. You can say an open circuit is equivalent to resistance of infinity. So if we construct this, we have a voltage difference of infinity between these 2 points, right? But doesn't matter really. For engineering purposes, we won't go there. We won't need that. So that's just a philosophical argument that we don't necessarily pursue. Okay, so a current source is a device that wants to maintain a certain current through it, and it can handle any voltage across it. And as I said, you can't really buy a current source. You can buy a voltage source, but you cannot buy a current source. But as we will see, there are some devices and some circuits that can be modeled as a current source. And that becomes a very nice and useful modeling method for such devices and circuits. Okay, let's see. Let's look at some examples here. Okay, so let me give you an example that you might find interesting. So here's my cell phone. And you know that to charge the cell phone, we're going to take a charger and we're going to plug this into the wall. And then we'll plug this into the cell phone. There's a battery in here that needs to be charged. So if I have a battery that needs to be charged, so here's a battery inside the cell phone, and this needs to be charged. Do I want to connect a voltage source to this battery to charge it? So here's a voltage source, another battery, right? And I just go ahead and put a switch here and connect them together. Would that do? No. That will dramatically shorten the lifetime of the battery inside the cell phone. Because, in a sense, we have two voltage sources fighting each other. This voltage source says you need to have a voltage of 3 volts. That battery says, no, I'm discharged. I have a voltage of 0.5 volts. So in that fight, that battery gets damaged. So in practice, what we have to do is, so we don't do this. Inside the charger, that's not what we do, okay? Or rather, inside the phone. So inside the phone, we take the battery that's inside the phone, and we try to charge it by a constant current over time. So there's a constant current, a current source, that is built using other devices inside the cell phone. And when that current is turned on, we keep injecting a certain current into the battery, and the voltage across the battery gradually goes up as it charges. And when it's charged up completely, we stop the flow of the current. So, in fact, inside the cell phone, there's a mechanism. It measures the voltage across the battery, and once that voltage reaches a certain threshold, it turns off this current source so that we don't overcharge the battery and damage it. Similarly, when the voltage across the battery is low, as the voltage goes down, you see that the number of bars on your cell phone for the battery goes down, and that's how it's measured. So this is an example of how a current source is useful in practice. This concludes the lecture today. I will see you next time.